All right, and I'm Matt. As Wojtek said, I'm currently a SIG chair of Scalability, and I also work at Google. All right, so let's jump into TLDR. Wojtek?
Okay, so what do we work on in Scalability? So there are basically 5 main areas that we are focusing on. First one is like defining what scalability really means and where we should be heading towards. Like what are the aspects of the system that should scale and to what targets those should scale. The second thing, we will be talking more about, we will be giving more details about each of those like in the later part of the presentation. So this is just like the summary. So the second part is basically monitoring and measuring where we currently are with the system. Third one is about contributing or coordinating the actual improvements to the Kubernetes. Fourth one is ensuring that we don't regress in terms of performance and scalability. And the fifth one is coaching and consulting community, like people from other SIGs or other contributors that want to ensure that their features scale. They want to do some tests and they don't know how to do it and stuff like that. Probably one thing worth mentioning is that you shouldn't confuse it with SIG autoscaling. SIG autoscaling is basically responsible for scaling either horizontally or vertically your applications or your cluster. This is like a different SIG and a different set of people. Okay, so let's go into more details. So if you ask users or customers what do they really want, and if they want Kubernetes to actually scale, they for sure like answer yes. We obviously want the scalable clusters or large clusters or something like that. But like if you try going into a little bit more deeper and details and ask them what exactly they want to really what exactly should scale in Kubernetes, they don't really know. And they don't really want to know because it's kind of an infrastructure for them, and everybody generally wants to assume that the infrastructure they are using underneath, which in this situation is Kubernetes, really works. And they don't want to understand all the gory details of the system. So in order to define what scalability really means for Kubernetes, we need to go take a little bit different path. So let's maybe look what Wikipedia says about scalability. So I'm probably not going to read all of that, maybe just the first one. So it's saying like scalability is a property of a system to handle a growing amount of work by adding resources to the system, which is pretty much useless definition from our point of view. It doesn't really provide any direction like how we should be thinking about scalability in terms of Kubernetes. So we need a different approach. So what we did like 5 years ago, when we were a little bit less than 5 years, when we were right before releasing 1.0 version, we defined scalability as a size of the cluster that we actually support. But it's not even close to actually the whole story. So yes, we do support like currently support clusters with like up to 5,000 nodes, but that's not all. Like scalability, like there are many aspects and many dimensions of scalability. And if you think about scalability for Kubernetes particularly, you need to think about many other aspects. So not only the cluster size. So what we did is like we defined this concept of like scalability envelope. And what it basically means is that like I don't want to call it cube, it's like a subspace with like a number of different dimensions, like size of the cluster or number of pods in the cluster or number of secrets or number of services and so on and so on. And this subspace that is bounded by this envelope is basically defines configurations of the cluster where when the cluster is actually happy, whatever that means, we will get to that. But it basically means that if you are within those boundaries, your cluster should work. So unfortunately, like computing how this envelope looks exactly is really complex. Are you aware of like this Kinevin framework? Any of you? So basically, it was defined like in like tens of years ago, but it basically divides the problems that exist into like 5 different categories. So simple problems, complicated, complex, and 2 more, which I actually forgot now.
Chaotic,
but like, sorry?
Chaotic? Or?
Chaotic and 1 more.
Else, yeah.
But basically, like there is like a difference between complicated problem and complex problem. So complicated is basically a problem that based on like experience and knowledge and some extended analysis, like can be solved, and there is like a right answer to that. Whereas complex is basically a problem that there are a bunch of unknown unknowns, and like the cause-effect reasoning can only be done like after we actually know what happened. So it's exactly this case, because like just looking into like this subspace that I pointed, it's pretty much impossible to say like whether it will work, the cluster will work or not. Obviously, like there are obvious points in this subspace where we can do that, but like for those closer to boundaries, it's actually pretty much impossible. But even if we would be able to like test all the possible configurations, we still need to be able to answer if that particular test was successful or was actually a bad one. And how we do that? So we are getting to the like what scalability really means for Kubernetes. So how do we define scalability? This one is actually a framework that we are using pretty widely in many different places. In Google, but not only in Google, generally in the world. So we are basically defining scalability based on like 2 main core concepts. The first one is like SLI, which is service level indicator, which you can think as some metric that is measured within your cluster. And SLO is like service level objective, which you can basically think about as that metric plus some threshold. And what we are saying is that the cluster scales within a given conditions if all the scalability SLOs are actually satisfied. So if all those metrics that we measured across this run are within the thresholds that we defined. Okay, so how should we choose the appropriate, how should we define appropriate SLIs and SLOs? So I think I already mentioned it, it's like if we ask the customers what are the things that they really want to be within some boundaries, like they probably, or in majority cases, they won't be able to do any reasonable answer, or they don't even want to give that answer because they don't want to know these details. But actually, if we ask a very specific question, like for example, how fast your pods should start, like pretty much everyone will be able to give some answer. Like those answers may obviously differ because like the use cases the customers or the users have are different, but they will give you the answers. So what we want to do is basically we want to come up with those proposals for metrics ourselves and just use users to define the thresholds that will be satisfying for them. So how to choose those SLIs and those metrics? And what we do, where we are getting is this concept of like product surface. So product surface is basically a feature set and API surface and stuff like that of the product. In this case, it's Kubernetes. So it's like the concepts that Kubernetes supports and the features it has and stuff like that. And basically, the SLIs are supposed to somewhat cover the product surface that is interesting for users. Okay, so how we are defining the SLOs, or the SLIs first, sorry. So there are like a couple of principles that we need to keep in mind to make the SLI and SLO like usable. So the first one is they need to be very precise and well-defined. Why it is so important? It's like imagine, or maybe let's use the example that from the real life. So when we were announcing like 1.0 version, we said like that one of the SLOs for Kubernetes is actually that API calls, like 99% of API calls will finish within 1 second. But what that really means, like it's so ambiguous that I bet that if I take any one of you and you will provide like your understanding of that, and we'll take my understanding. Those will be different. So you may probably think that I'm working on that like for 5 years and thinking about that. So it's because of that. But I actually bet that if I take any two of you and take your definitions, like your interpretations of that, it would be exactly the same. There will be different. And why it is so important? Imagine that as a user, using your interpretation of this like badly behaved SLI or SLO, the cluster doesn't scale, it doesn't meet the SLO. And in my interpretation, which is different, so the situation like can happen, it actually scales. So we are getting to the point that you are saying this cluster doesn't work because it doesn't meet SLOs. I'm saying that it does, and we are both right. So that is obviously pretty bad situation. So that's why we need to have them very precisely defined. The second thing is, or second principle is that they have to be user-oriented. And I think that's pretty obvious. So the last thing that you would like to have is like having an SLO, which requires a bunch of maintenance, ensuring that we are not regressing, refining it because like the system is changing underneath and stuff like that. So it requires a bunch of effort and work, and no user really caring about that. So that's really bad situation to be at. Maybe it doesn't hurt the problem, but it doesn't hurt the product, but it actually means that we are wasting a bunch of work. The third principle is that we want to make them consistent with each other. I think that is also pretty obvious. We don't want a user to like really need to understand like everything from scratch for every single SLO that we have. So that's also like making them consistent. It basically means that like they need to understand kind of a framework once, and then understanding every single one of those should be relatively easy. And the fourth one is that they need to be testable. So ideally, we actually want them to be measurable in any single live cluster, no matter if it's like we are doing tests or running production workloads there. And we are trying to build the SLOs exactly and SLIs in that, but sometimes it's like very tricky. So in certain situations, we allow the SLOs to be only measurable in benchmarks, but this should be like the last resource and should be very rare and more like treated as an exception than as a rule. So what are the existing Kubernetes approved scalability SLIs, SLOs? So there are two of them currently. One is the API call latency. I I think it's actually worth mentioning that even though it's like pretty long definition here, it's not exactly the whole definition. It's still like approximation. We didn't want to put like couple lines of text in the slide because that wouldn't be very readable. There is a link to the page with SLOs like later in this presentation. But basically what we are trying to say is that like, it's roughly what I mentioned before. So like 99% of like API calls finish within some time. But basically there are a bunch of details that are not really mentioned here. Like, what about webhooks, for example? Like, obviously you can install webhooks in Kubernetes, and if your webhook will be sleeping for 5 seconds, then it's obviously we are not able to meet those SLOs. So there are details like how we are treating and what we are assuming and what we are excluding from the time we measure and stuff like that. So this is like some approximation. And the second SLO that we have is like for pod startup time. So we are saying that in 99 percentiles it should finish within 5 seconds. But again, it excludes things like time to run init containers, which can be pretty much unbounded. It excludes time to pull the image because it's something it is completely out of our control and stuff like that. So those are approximations, like the exact definitions are on the page. We have 5 more SLIs and SLOs that we worked pretty hard with like other SIGs, mostly with networking and storage. They are defined. We are already measuring all of them in our test, maybe without the DNS programming latency. Or
we are almost there.
We are almost there. We will be there probably within the next like 2-3 weeks or something like that. They are not yet approved because first we didn't do a full round of like meetings or like consultations with users. Like we know that those are the things that they really care about, and then this was consulted with users. We don't really know yet we know roughly where we are now based on the tests and which we are measuring in terms of like the values where we would be able to satisfy the thresholds, but we need to consult with users like and if those thresholds are actually something that is satisfying for them. So this is something that we need to do, and that is something that is mostly the thing that is blocking us from approving them. This is the link that I mentioned where all those things are defined, are written down, like all those SLIs or those principles that I mentioned before and stuff like that. Okay, but it's still not exactly what we want, because obviously it's not that we can guarantee those SLOs in every single, no matter what you do. So it's pretty obvious that if you throw billion of pods into your cluster, it won't work, and we won't be able to satisfy those SLOs. So what we did is we introduced this framework of like you promise, we promise. So we are saying that if you promise that you configure a cluster correctly, you stay within those like boundaries from Scalability Envelope that I mentioned. So as an example, if your cluster has like less than 5,000 or at most 5,000 nodes, less than 30 times number of nodes pods and stuff like that, if your master is provisioned correctly, has enough resources and stuff like that, only then we actually can promise you that the scalability SLOs that I mentioned before will be satisfied. So this is the framework. This is how exactly we are defining it, and we are providing what we are providing to users. So computing, like as I mentioned, computing this, how exactly this envelope looks like, is very complex, but fortunately we don't really need that. So it's generally enough to have some approximation for that. And to do that, we are basically decomposing this scalability envelope into a number of somewhat independent dimensions. So for example, we are saying that like number of nodes has to be at most like 5,000. That total number of pods has to be at most like 30 times number of nodes, and so on and so on. And we kind of decompose them. It doesn't mean that this is exactly how the scalability envelope looks like, but it's good enough approximation, and it's what is much more understandable and for users and much more easier to talk about. And this link contains, like, the link that is here contains, like, what are the dimensions that we are currently thinking on, and what are the limits that seem to be safe to use according to our tests. Yeah, so one more thing to mention here is that, like, the fact that we define some SLOs doesn't mean that we're done. So first of all, like, the product or the Kubernetes is evolving. We are adding new features. So probably majority of them should be covered by some SLOs, because if we are creating those features, probably someone really cares about them. Second, the fact that we are adding new features in many cases, like, affects the existing SLOs. Like the example is what I already mentioned, is the webhooks. When we defined, like, API call latencies for the first time, no one even was thinking about webhooks. But obviously they are affecting, like, the latency of API calls. So there should be, like, a constant loop, so that we are defining SLOs, we are running scalability tests, we are improving some performance of some components, we are talking to users, what they think about it, what are the other things, new things that they really care about it, and we should go back to, like, and refine existing SLIs, SLOs, or add new and stuff like that, or maybe even remove some of those if no one really cares about them anytime longer. Yeah, so that's roughly what I had about scalability, or about defining scalability. One thing to mention, if you are interested in a little bit more details, I was giving a talk on previous KubeCon in Barcelona. The whole talk about, like, this aspect, so you can probably find the recording on YouTube, or yeah. And I'm good. Yeah. Yep. Passing the mic to Mark now.
Thank you, Wojtek. So we can say that was a theory. Now let's focus on practice, right? So in the couple next slides, we'll be introducing you to all the tools, all the processes, all the means we have that we use to keep Kubernetes scalable. Right, so starting with automated tests, right? I guess it shouldn't be a surprise to you that we do run tests to make sure that Kubernetes scales. And as everything in Kubernetes, we use the test infrastructure for that. So the Pro for running continuous job, also running pre-submits, and using test grid to present the results. This is a screenshot of our SIG Scalability test grid. So what kinds of tests do we have? We can, like, divide them into some groups. I will start with correctness. I think this one is the less interesting. So basically in Kubernetes, there is a concept of correctness tests. These are release blocking tests running on, they are like end-to-end tests running on 4-node cluster, if I remember correctly. And what they do, they basically check that most Kubernetes functionalities work as they should, right? Like end-to-end, in an end-to-end way. So for example, if a deployment is created, the pods for that deployment should be created, right, and run. If I create a service, I can, like, ping a pod which is part of this service, and stuff like that. So what we do, we take these tests and we run them at scale of 5,000 nodes to make sure that everything works and nothing breaks at this officially supported scale. The more interesting part is actually performance tests, which are using the framework that Wojtek described. So what we do, we stay within the the scalability envelope, which is basically we stand within the official scalability limits. So for example, we test 5K node cluster, we stay below the 30 pods per node average density, we don't create like too many namespaces to stay within the limits, and then we test that all scalability SLOs are satisfied. Currently we have 2 tests. One is called density and the other is called load test. We are working actually on merging them together. What they do, briefly, so density test was created to measure pod startup latency. What it does, it first loads a cluster with 30 pods per node on average. It waits for all the pods to be created, and then it creates additional 1 pod per node on average and measure how long it took to create this pod. So we measure like 99 percentile of the pod startup latency, and we expect this time to be below 5 seconds. Load test is similar in a way, because it also loads cluster up to 30 pods per node, but it does it in a much more sophisticated way. So in addition, we are creating services. We are not only using deployments, we are using daemon sets, stateful sets, jobs. We are creating some secrets, config maps. And in addition to just creating, then we have a scale up, scale down phase, where we are like randomly scaling like deployments, jobs, and stuff up and down to generate some pod churn. And yeah, after that, we also like measure the scalability SLIs and verify that they are within the limits. And like the third category, other, so basically everything else. So we have some storage tests, we have some benchmarks, for example, scheduler benchmarks, where we just run an API server and scheduler and verify various things like throughput. We have some micro benchmarks where we are testing performance of like some single methods, maybe some important methods in Kubernetes, and yeah, stuff like that. Okay, so we can also, like, these were like kinds of tests. We can call these slides present types of tests. So we have some release blocking tests. One of the release blocking tests is performance test, so load plus density, running on 100 node cluster. These tests run every hour, I believe, or so. And it's a very important signal, especially now, like during freeze, and to make sure that everything works. But like 100 node, it's not actually, it's far from the officially supported 5,000 node scale. That's why we also run 2 tests, correctness and performance, at this 5,000 node scale. We run them daily. Why? Because the performance test, so to create 30 pods per node in such cluster, that is like 150,000 pods in total, and do all these operations, so to scale them up, down, and delete, it takes about 12 hours, right? Correctness tests, they also take about 4 hours, so in total that's, plus if you add some headroom for some timeouts, that basically they take whole day. And when it comes to non-release blocking, we have some Kubemark tests. I'll be talking about Kubemark later. This is our framework for simulating large clusters for performance test purposes. And like all the other kinds of tests, so storage benchmarks, micro benchmarks, are non-release blocking. You can find them all in our scalability test grid. Right, and other category is pre-submits. So whenever you send a PR to Kubernetes or Kubernetes Perf-test, which is our repo where we host almost all of our tools, part of the Kubemark is hosted in Kubernetes. These 2 tests will run as a pre-submits. So we run performance test on 100 nodes. Oh, I forgot to mention that. So what we do, we run Kubernetes on GC in our tests, or Kubemark, which I will describe in a moment. And we also test performance Kubemark 500 nodes. And similarly for the Perf-test repo. All right. Next tool is our performance dashboard called Perf-Dash. It's a custom-made tool that basically, I think I have it here. So long story short, is a dashboard that visualize various metrics from different continuous integration test invocations. And the idea is that basically you can compare how some metric changes across different runs. It's a primitive tool. Like if you check code, like Perf-Dash code, you will know why. But it's very powerful. I can show you some examples. So it can answer your question about either, it is very helpful when it comes to performance regression debugging, or if you want to find something about various perf-related Kubernetes characteristics. So for example, what is the current scheduler throughput in the 5,000 node cluster, right? We can check that in perf-dash. So here we have test, that's GC 5,000 nodes, and like each point here represents one run, right? So we get a point every day. As we can see, it's around 100 pods per second, except for this part here. Here we actually had a regression, and thanks to perf-dash, we were able to identify it, and folks from SIG scheduling fixed that, and we are back to 100 per second. All right. Other example, what is the API server memory usage, right? Oh, so as we can see, it went up recently. We should look into that. Or, for example, for performance regression debugging, in general, it's useful because you can usually find a place in time when something happened. Here's an example of one of the regression where we used perf-dash extensively to actually pinpoint the issue and fix it later. All right. Another tool is the Go profiles that we gather in our tests. So basically what we do, we try to gather from all control plane components, so Kube API server, etcd, Kube scheduler, Kube control manager. What kind of profiles? So the standard ones, so CPU, memory, and for some of them, mutex profiles. These are useful for sometimes for debugging regressions, especially like if someone changed code and something now started taking like much longer, then you can take a look at the CPU profile. And now you see, for example, that, hey, now we are spending 80% of the time in this single method, right? So most likely something is wrong there, and we should optimize that. And yeah, the flagship tool of SIG Scalability, ClusterLoader2, it's a bring your own YAML load test tool. Basically, before ClusterLoader2, our end-to-end scalability tests were written in Go, and that was hard to maintain, hard to extend for many reasons. Also, it was impossible for like people outside of SIG Scalability to contribute or like to create their own scale test. So we had this idea that it should be much simpler. Basically, you should just like define your workload. So what do you want to? You should define a state that the cluster should reach, and this tool should bring a cluster to that state, right? So that's the declarative paradigm. That was like main assumption behind ClusterLoader. I will be explaining that in more details in a moment. In addition to this declarative part, of course, there's like a bit of imperative part because it's necessary for load testing. So we need to specify how things should happen. For example, what is the throughput, what is the QPS with which we are creating the objects, and also like what should be measured during the execution. So for example, the scalability SLIs. And in addition, it provides extra observability for free. It sets up the Prometheus and Grafana for you. I'll be talking about that also in a second. So when it comes to ClusterLoader API, it's actually very simple. So the main resource is a test, and test consists of steps, right? Steps are executed serially, and like, what is step? So step, for example, can be create 30 pods per node, or start measuring API call latency, or stop measuring API call latency and verify that it was below this threshold, right? Or create this other object and stuff like that. Right, so yeah, that's a step, and how is it implemented? So a step is either a collection of phases. This is this declarative part. So basically, phase defines a state a cluster should reach. So let's say 30 pods per node, 10 services, and stuff like that. Or measurement, which is basically anything else. And usually we use measurements to measure something or wait for something. And I will show you an example I created for my other presentation. Right, so it's not only YAML, it's also like Go templates, which allows you to define some variables and do some crazy stuff in YAML, like loops and stuff. Not in this example, but it's doable. Right, so like it's a very simple example that will create 5 pods per node, and then scale up deployments. So we'll create these pods using deployments. We can go like step by step maybe. So first we are starting some measurements. We will be measuring API call latency. And we have this measurement for waiting for pods. And it will be targeting all pods with this app is my deployment label. So then we are creating deployments. Tuning set is this like imperative part, so basically how fast it should happen. We'll be using uniform 5 QPS. And we are pointing to the deployment YAML, which is another YAML. So it's like a regular YAML, deployment YAML, but again, you can like use some templates here, right? Some name will be created for you, and you can also like pass your own parameters, like number of replicas or requests. You can do like anything you want here, right? So that's very generic. And here we are passing like number of replicas and requests, CPU memory requests. Then we are waiting for pods to be created. Then we'll scale deployments up by 2 pods per deployment. Again, we'll wait, and then we will delete. And at the end, we will check whether API call latency was within thresholds or not. Right? That's a very powerful tool to do load testing. You can easily like reproduce your workload here and test it, and we like encourage you to do that and share these YAMLs with us. We are looking for inspirations to extend coverage of our performance testing. All right. Other features of ClusterLoader, including but not limited to auto-managed namespaces. So basically, ClusterLoader will create namespaces for you. We'll also delete them after the test. This is like one reason for this feature is to make sure the tests are hermetic. So we can run the same test multiple times on the same cluster, and they won't be interacting with each other. Chaos Monkey, so it's a feature that randomly kills nodes. Basically, we are simulating node failures. That's useful sometimes because that happens at large scale, right? So crash looping components detection is a new one. So in addition to like validating some SLIs, SLOs, we are also checking whether there are any system pods that started crash looping, right? Sometimes it happens, even though all SLIs are satisfied. Probes, they were mostly created to implement the new network SLIs. So for example, we have these probes that are like pinging each other and measuring the network latency and stuff like that. Prometheus monitoring, we'll be talking about that in a minute. Templating, you already seen a bit of that. Tuning set, so basically saying how fast objects should be created. All right, and here are some links. So all code and documentation is in our Perf-test repo under the ClusterLoader2 directory. And if you are looking for the load and density test definition, they are also there. All right, so next thing is Prometheus and Grafana. So as I said, this is integrated into ClusterLoader. We are just adding one flag, and ClusterLoader will set up all this Prometheus stack for you. And there are like 2 ways of using it. Either you can use it on the live cluster with ClusterLoader running. So basically, you can just do a port forward to the Prometheus or Grafana pod. Or we also have this feature where ClusterLoader creates a snapshot of the disk with Prometheus database. And we can recreate Prometheus from that snapshot after the run. And this is very useful for debugging regressions. I have an example here. So this is maybe I can make it bigger. Right, this is an example of one of our 5K node performance test run. And this is how our Grafana dashboards look like. So we have like requests coming from ClusterLoader, API call latency, and many more things like unhealthy nodes. We have like some routines in Kube API server, a lot of stuff about like watch, performance, in-flight requests, request rates. It's super useful when you need to debug, like when something goes wrong with cluster. Yeah, some memory usage, CPU usage, and stuff like that. All right. All right, so Kubemark. As I said already, is a tool for simulating large Kubernetes clusters for scale testing purposes. So the idea is that it's actually expensive to run these large-scale tests, right? And in scalability, what we really care about mostly is the control plane, right? So the master node. We don't really care about what happens inside Docker, yeah, to some extent. But yeah, that was the idea that maybe if we kept the control plane as it is and looked for some saving on the node side, started simulating them, we could do it much cheaper. And that's true. For example, as you can see, to run 5K node scale tests, you need around 5,000 vCPUs, right? And it comes mostly from the nodes. And to run Kubemark, you only need 700, right? So that's about 10 x10 difference. And as I said, the idea is so we are leaving control plane as it is, because that's what we are exercising in the test. And we're introducing this concept of hollow node. So we'll be simulating nodes. And a hollow node simulates a node and consists of the following containers. So we have hollow kubelet, which is a real kubelet, and we are faking some of the kubelet components. So, for example, instead of Docker, we are using fake Docker, right? And what fake Docker does is whenever you ask it to run a container, it will just reply, hey, I run this container, right? But it will do nothing more. Hollow kube proxy, which can run in different modes. I will explain that in a moment. And node problem detector, which is a standard container running on every node in Kubernetes. And when it comes to Kubemark modes, everything boils down to the way the hollow kube proxy works. So one way is you can run hollow node without kube proxy, but that's not a good idea if you want to scale test Kubernetes, right? Because kube proxy actually contributes a lot to the load on the API server in general, right? Because for every endpoint change, for every actually it's starting with pod changes that are part of some service, endpoint controller will update the endpoint object, and then this update is sent to every node, right? To kube proxy to process and to program IP tables. So if you get rid of that, then actually it will simplify too much, and that there won't be much gain in like doing such tests. So what we do, we either run kube proxy with real proxy or with fake proxy, right? So proxy is just like this part of kube proxy that is responsible for, you can say, programming the network. So for example, there is like IP table proxy that processes all the endpoints updates and services updates and writes IP tables. So what we do is similar to hollow kubelet. It's a real proxy, but we are faking everything everything else, right? So we are mocking IP tables, scuttle, and stuff like that. So it still like computes all the changes and all the IP tables it would normally written, but basically it just sends them to some mocked interface of IP tables. So they're like not written down. And the other option is to use fake proxy, which basically, so there are like still watches for endpoints and services, but we are not computing anything in the kube proxy. And right, so that's the idea, right? So we will have real control plane, real master. We will have these containers for simulating node. So now we have this problem. We need to run a lot of containers, right? What do we do? If we only had a tool for that, right? I can see that some of you got my joke. That's good. Of course, we use Kubernetes for that, right? So that's actually confusing very often for a first-time Kubemark users. Kubemark actually is two clusters, right? You can start either way, but let's say you started with the empty cluster, just master, and that will be Kubemark master. And then you have another cluster, well, you will run all these hollow nodes, right? And you configure the hollow nodes to connect to this Kubemark master, and that's it. You have a fully functional Kubemark master. So like using, let's say, 10 nodes, you can simulate a few hundred node cluster, right? And from the client perspective, everything is transparent because client talks to this Kubemark master, and it sees a cluster with let's say 5,000 nodes, even though there are only like 100 in this real cluster. That's how we can save a lot. All right. So that was mostly it when it comes to the tools we have. Now, the other important part of our work as SIG Scalability is protecting from regressions. So scalability is sensitive, right? It's very fragile. Sometimes there are like changes that seem like totally innocent. For example, I don't know, bumping K-log to some minor version, right? What can go wrong, right? And then we discover that it totally breaks our scale test. And we've seen regressions coming from pretty much everywhere, from like Golang, operating systems, controllers, API machinery, scheduler, etcd, kubelet, and basically everywhere. So what do? We often we always debug them, and when it comes to fixing, we either do that ourselves or we triage to relevant SIGs. Some of the interesting regressions that happened recently. So we had 2 Golang regressions. One in Golang 1.12, which was actually released after we caught the regression, and then we spent, I don't know, a few weeks, right, debugging that to figure out what went wrong. We debugged that quite quickly, but it took some time for the Golang folks to actually figure out how to solve the problem, find the commit that broke the Golang's performance. And there was another Golang regression in 1.13. This time we caught it before, we started testing before Golang was supposed to be released, although it was released with the regression, right? Only starting from Golang 1.13.4, right?
4, yeah. Yeah, but those are only the recent Golang regressions. There was also a regression in 1.5 Go and 1.8 or 9.
Yeah, it happens a lot.
At least 4 of the Golang releases were initially broken, which basically shows how powerful Kubernetes is, because it wasn't caught by anyone else before. It's only when we decided to upgrade Kubernetes and compile it with a newer Golang version.
We are the biggest Golang client, right? You can call client in a way. The last 2 were related to actually memory allocation. I don't know about the 2 regressions before that.
One was that they broke the HTTP server, the HTTP part or HTTP server. I can't remember exactly. And the 4th one I can't remember.
Yep. So what usually happens, they change something in memory allocation path, which they even improve something at smaller scale, right? But you can see in this 5K node cluster.
The 4th one was actually broken or regressed Golang.
Because the single
CPU scheduler.
Single API server gets up to 600,000 coroutines, right? And they're allocating a lot, and that's when even tiny change in Golang can change a lot overall. All right, some other regressions. So operating system. There were a few in COS. I think this one listed here was that in our master setup we have 2 disks. One is the boot disk for all the logs and system stuff, and we have a separate SSD disk for etcd. And usually they should be independent of each other, right? So writing to one disk shouldn't affect operations to the other disk. But sometimes at the operating system level something can go wrong, and now the issue was that during the log rotate, so when there was really high throughput writing to the boot disk, the etcd disk got starved, and that was causing a lot of issues downstream the Kubernetes. And other stuff core DNS, I think this one was that some change in core DNS that was triggered by something else resulted in core DNS started using more memory, and then crash looping or stuff like that. And then when you have components like core DNS, so running a lot of nodes, which are crash looping, to restart their watches, they start sending very heavy list requests to API server, and that can cause a lot of problems. K-log, which I mentioned, Yeah, even like something like Klog can break scalability, right? I think that bug there was that they started producing more lines, so the log volume went up. Yeah, and it caused some other issues. Like recent one in Reflector Go. Actually, there was like a fix in Reflector Go. It was fixing like a problem with time travel. So Reflector is like this piece of code that basically allows you to use the watch mechanism, right? It has. So what it does, like it has this local cache, and basically it makes sure that this local cache will reflect that everything that is on the CDN and API server, right? And the problem with going back in time is like to start the watch, you need to list first, right? The resources we are interested in, and this will give you the resource version. And starting from this resource version, you'll be watching all new events, right? And then you're like the way it's implemented, you are basically restarting the watch from 5 to 10 minutes. And if there is like a lot of happening on the API server, or if your client is slow, it may happen that if you want to restart the watch with the recent resource version you got, API server may reply that the resource version is too old, right? I don't know about it anymore, like in my watch cache. So then you need to list again. And now the question is like, what resource version should we use for this relisting? Like, won't be getting into details, but there was like for the HA setup with 3 masters, it's possible that one master was lagging, and basically your request got to that master, and then you would get you will basically go back in time, right? You will get like events that you already processed, or like some old state of the system. So fix there actually revealed a bug in PagerGo, which is like very common utility in Kubernetes, right? I think.
Yeah, it's the utility for paginating.
Yeah, for pagination, right?
The list request.
That was like a very silly mistake there, but yeah. And there are like many, many more. All right, so Wojtek,
yeah, so
handing out to you.
The other thing that we are working on is either driving scalability improvements or like coordinating things that other SIGs are doing to improve scalability, or providing them requirements to their improvements, like to what extent, to what like level of scale or performance they should improve their components or their features. So I probably not going to like go into details into all of them. Like if you are interested in any particular one, I'm happy to talk more about any of those. We can maybe leave it for the question phase if there's something that is looking interesting to you. I just briefly mentioned them. So first one is migrating kubelet from polling to washing for secrets and config maps. So previously, there's this feature in Kubernetes that like whenever secret or config map is updated, all the pods that are mounting that as a volume or as a file in the node basically will get an update, like that will be updated. And previously it was implemented by kubelet as periodic polls, and periodic polls to check whether it's changed, and if so, like doing the update. That was migrating to watch in 1.14, so quite some time ago, but still like less than a year ago. So the things that I'm mentioning are pretty much what happened since last KubeCon. So somewhere since last KubeCon, that improved situation significantly, but we are not still where we would like to be. So we are looking into this problem. We are still looking into this problem, how to make it work even better. The new events API, this is an effort that is already lasting for 2 years at least, and it's still not finished. Like basically we have the API, the new API. We have the client implementation now that is reducing the load on the API server if there are a bunch of same events being sent from the same component. So for example, if the pod is crash looping, we are sending an event every single time. So those kind of situations, we change the API so that like we just send the update the event like every 5 minutes or every 10 minutes or whatever, something like that, instead of like writing it every time. We introduced this concept of like event series. But so far we migrated like only scheduler to the new events API. It's like, and the API is still like in beta, so there's still a bunch of work to be done here. Cheaper node heartbeats is pretty significant improvement. It's probably the most important from all of those mentioned here. So basically previously, like the only heartbeat signal that kubeless was sending it was sending like the node status updates every 10 seconds, and node status or node object in general can be huge. It can be like tens of kilobytes because of images it keeps, like, and stuff like that, and this was causing like a significant load on API server and on etcd probably even more. So what we did is we introduced this concept of like lease object, which is very small object, and it's only like, it can be used for like leader election, but it also can be used to like send those kind of heartbeats. And we changed the kubelets so that like it's periodically changing, periodically sending those small, very small, tiny little lease objects and sending node statuses only if something changes, or like every 5 minutes or something like that, just for kind of backward compatibility that it will be sent. And that like significantly helped. This is going to GA like in 1.17 release. Endpoint slice API, this effort was like more, we were taking part as consultants and like providing requirements and like advising on the design, but it was like driven by SIG network. Basically, they introduced the endpoint slice API, which allows you to shard, like previously we had for a service object, for a service in Kubernetes, we have a single endpoint object. So with like something like 5,000 of pods in a single service, or even less if their names were long enough or something like that. So we were hitting the limits of like size of the object in etcd that can be stored and stuff like that. So endpoint slice allows you, from performance perspective, to shard the service into, or shard the endpoints from the service into multiple objects, but it also allows to effectively implement other features like external endpoints, for example, for services. So while the motivation, like the most important motivation at this point was like performance and scalability, like we spend a bunch of time ensuring that it will also help. It will also be useful for other networking features that like they wanted to do at some point anyway. A bunch of like more local improvements in particular controllers. A bunch of improvements in API server itself or API machinery, like how we serialize object and to avoid serializing them multiple times for every watch independently, for example. That was a very recent change. Watch bookmarks is this concept of a special event type that we are sending over watch that can tell you like everything up to this resource version we already processed for you. The fact that you didn't get any object over the last minute, 5 minutes or whatever, means not that we forgot about you, but it's just nothing that you are actually requested via your like label selectors or field selector and stuff like that. And that basically allows to significantly reduce the number of those out of history errors where watch was like the last resource, the last object, or the resource version of last object that we actually observed was like too far in the past. And the last thing from the most important improvements is like introducing concurrent reads in etcd 3.4. So basically, previously, whenever we are doing a read, or actually I should say like expensive read in etcd to the etcd, so like listing, for example, listing all pods or listing all nodes or something, that was actually blocking any other operations in etcd. And what they did in etcd 3.4 is that we are blocking only for very short amount of time to pretty much do some copy on write copy for the index they have, and then it's being served from there. And it basically improved latencies of like write requests under heavy list requests routes, list requests traffic by like something like order of magnitude or even a little bit more. There were also a bunch of like other, maybe you shouldn't call them improvements, but changes or like things that happened in the last 2 quarters or something, including like extending test coverage to other resources, implementing the currently work in progress SLIs, improvement to Kubemark, improvement to ClusterLoader, and so on. Like, one thing that is probably very worth mentioning here is that we are working on this like scalability approval process. I'm not sure if you like heard about it or not. So as part, like we kicked in this process of like production readiness review. So as part of every proposal or any proposal for any feature to Kubernetes, we are going to require, probably in the quarter-ish from now, we are going to require the author of this proposal to also fill this production readiness questionnaire, where they will have to answer questions like how to make your feature like production ready, how should it be monitored, what are the metrics that should be added, how it should be upgraded, can it be disabled, and stuff like that. And as part of that, we will also have a section about scalability. So the authors of the feature will have to think about how their feature will influence scalability, to what targets that particular feature should scale, want it to break the existing features in terms of scalability and stuff like that. So that is something that we are currently working on. We are in the pilot phase where we took couple existing proposals and working with their authors to validate if our proposal for the questions actually makes sense, if they are useful, and if they are not like too hard to understand, and at the same time being meaningful for us to catch something. Yeah, and I think that's mostly it, like how to get involved if you are interested. We are trying to keep at least a couple open issues in both like KK repo and Perf-test repo. If there isn't anything that you are interested but you want to work on something else, like please ping us on Slack. We have a bunch of other ideas, we just don't have enough time to file issues for every single one of them. So we are more than happy to talk about you if you have anything that you are particularly interested in or would like to work on. So
yeah, as Wojciech said, some of the issues are tagged with the good first issue tag, and basically
I think all of them are tagged with help wanted.
Yeah, maybe. But basically these are the issue we believe they are like a good starting point for anyone who wants to contribute to SIG Scalability.
Yeah, and also we have those like bi-weekly public meetings where if you have any questions or you want to contribute or you don't know how to use something or whatever, like feel free to come and ask those questions. Yeah. Do you have any questions? Like, I think we have a lot of time, but I think that's probably the most important part, because like the goal was to like ensure that you actually leave this with what you wanted to hear, not that we told what we wanted to present.
Yeah.
If not, we can also take them offline after. Going once, twice. Okay, thank you very much.
Thank you.